We are going to take a look at adding vectors, but now we're going to go into two dimensions. Everything we've looked at to this point has either been all vertical or all horizontal, and we've never really combined the two. But now we're going to take a look at something that is not all in one direction. Okay, and so, well, let's start with a simple problem. Okay, start simple. We can make it complex from there. Suppose, for instance, that I want to describe the displacement of somebody who first walks this way, say straight east, 35 meters. Okay, 35 meters east. And then they turn and they walk straight south another 20 meters. And I want to know their displacement. Okay, and remember, displacement is how far they are from where they started. So what I really want to know is I want to know this. Okay, this is called the resultant vector, and this is the sum of two vectors. And it's really not that hard to find. I mean, you guys have all taken a little bit of geometry, had a little bit of trig, and so you guys can all tell me the Pythagorean theorem, and you can say a squared plus b squared equals c squared. Okay, well, we're gonna rewrite this a little bit. We're gonna say we're gonna keep a and b the same. A squared plus b squared equals r squared. R for resultant. Okay, and that'll give me the magnitude of this vector. Okay, the Pythagorean theorem will do that for me. Now, I'm also going to need to know this angle. Okay, so if you ever see me write this thing, this is the Greek letter theta, and it's just the common symbol that we use to represent angle measures. Okay, so this theta we have to know, because remember, a vector includes both magnitude and direction. So if we just know magnitude, it's not enough. We also need to know an angle. And southeast isn't specific enough, right? We used to be able to just use sign. Plus is positive, minus is negative. But when we're going this direction, well, we're positive in the x and negative in the y, so we got to combine that. Okay. And I don't know what you guys remember from geometry or trig, but if this is our system and this is the x-axis and this is the y-axis, this is 0 degrees. And we measure angles from 0 degrees in a counterclockwise motion. So this is 90, this is 180, this is 180, this is 270, and so this is 360 up here again. Okay, so 0, 360, we're just going to keep going in circles. Alright, so how do I find this thing? Well, for now, we might just concentrate on magnitude, but there's three trig functions, right? The sine of theta, the cosine of theta, and the tangent of theta. And sine is opposite over hypotenuse. Okay. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent, so it doesn't involve the hypotenuse at all. So if I'm looking up here at this function and I want to know this angle, okay, relative to this, I can say, okay, well, I know an opposite side. This side is opposite of that angle. This side is adjacent to that angle. And so we can say the tangent of theta is equal to the opposite side, that 20 meters, divided by the adjacent side, the 35 meters. Of course, I don't know theta. I want to know theta. So I don't use the tangent function because the tangent's applied to the theta. I have to use the inverse tangent function. It's a lot like square rooting a square. So the inverse tangent or arctangent, I'm going to say theta equals the arctangent, and on your calculator that's tangent -1 of 20 over 35. Okay? So there's some basic things on how to do that with your calculator and how to use the Pythagorean theorem. But let's actually take a look at what's going on with vectors, right? Vectors have a magnitude and direction, so they don't care where they're at. And this is one of the cool things that we know about vectors. Vectors can be slid around the plane. Okay? And here's what I mean by that. Since a vector just includes a direction and a magnitude, which essentially is a length, right, or a force or whatever, but we represent the magnitude of a vector with the length. So here's a vector. Okay? Now I'm going to take that vector and I'm going to move it from here to here, and from there to there, from here to there. I haven't changed anything about that vector. Vectors don't care where they're at. Okay, vectors just move around the plane happily. They just tell me a direction and they tell me a magnitude. So if that's one vector, and I've got another vector, say that's similar to it, but points in a slightly different direction. So let's say I had two people pulling on a block. So let's get a block, and here we go. Here's a block, two people are pulling on it, and I want to know what's going to happen. Okay, well, clearly it's going to move in some general direction this way, okay, because they're both pulling a little bit up, but I'm not really sure if it's going to go left or right. And so the way we deal with this is what we do is we slide the vectors around tip to tail, so that the beginning of one vector is at the end of the first vector. So it doesn't matter which way you pick, and in fact I'm actually going to do this two ways. Okay, we could take this one, and since it starts here, we could slide it up to the tip of that vector. So we went from the tip of this one to the tail of that one. Now what we do then is we draw our resultant vector from the tail of the first one to the tip of the last one. And so I'm going to make this a different color, and let's see, we're going to start here, the tail of the first one to the tip of the last one. And from that we can see, yes, the majority of this is up, but it's also going to go a little bit to the right. Now we can actually measure the lengths of these things and the angles, and we can tell everything we want about that resulting vector. Now I'm going to show this to you in another way. Okay, this vector originally was down here, and so I'm going to have a copy of it. I'm going to leave it down here. Okay, and this vector, I'm going to do the same thing. I'm going to clone it. I'm going to move it over to the, whoops. Well, I used to be able to do that. Alright, there we go. Move it over to the tip of that one. And you can see everything comes together right here. Okay, so it doesn't matter which vector you pick to move around. This is the parallelogram method of vector addition, but either way, when you go from the tail of the first one to the tip of the second one, we get this resultant vector right here, and we want to know everything about that. Okay, so graphical addition just says, let's slide the vector so that the tip is on one and the tip of one is on the tail of the next. Okay, add vectors tip to tail. Now we can actually do a little bit of math with this. I know that makes you guys super excited, and so I want to know everything there is to know about this vector, which means I want to know its magnitude, and I also want to know its direction. Okay, and so to get that, we're going to use a protractor. Whoa. Okay, and protractor is pretty easy to use, right? You put the 0-degree mark right on, or the 0, the center, right on where everything starts. Okay, and my protractor is a little bit big, and since I can magically change that, at least I hope I can. Hey, look, awesome. Okay, then I can say that my, let's go ahead and label some vectors. Okay, let's call this vector, whoa, let's call this vector A and this vector B. Now B's are really over here, but we drew it up over here so we could add them. Okay, and so this is also, I suppose, vector A, and this is also vector B. Okay, so if we grab our protractor and put it right where everything starts, right here, okay, then we can see that vector A is pulling at 100, well, we start at 0 and measure this way, so 35, 6, 7, 37 degrees. Okay, and we can see vector B is clear over here at 140, looks like 146 degrees. Okay, let's see, let's go ahead and make this thing a little bit smaller. Okay, and that way I can see, yeah, it looks like 146 degrees. Okay, so vector B is 146 degrees. Now, what can I do with that? Okay, the other thing I can do with that do I care how this one is relative to start or relative to A? Well, I might care how it is relative to A, because how would I get this, unless you have a smart board, how do you actually construct vector B from here over to here? Okay, so I'm going to move this out of the way for now. Okay, I'm going to move my resultant out of the way for now. I'm going to move this guy out of the way for now. And so now I just have my two vectors, A and B, and I know this one's at 37 degrees, I know this one's at 146 degrees, but what I want to do is I want to get vector B from where it's at over here to the tip of vector A. Okay, so instead of measuring my angle based off 0 degrees, which is what I did for vector A, I'm going to measure the angle between vectors A and vector B. Okay, so I grab this guy, and I think I can do this. Yep, I'm going to rotate him up until he lines up with vector A. And then I can see that this is 10, 20, 30, 40, 50, 60, 70, 80, 90, 109 degrees. Okay, and so that's really what I'm interested in. I'm interested in these two vectors are 109 degrees apart. Okay, and so then if I take my protractor and slide it up to the tip of this vector, and I put my mark at 109 degrees, which is right here. Okay, now I know about where vector B is going to be, but I need to know one more thing about it. I need to know its magnitude. Well, remember, the length of the vector represents its magnitude, and so what we're going to do is we're actually going to grab a ruler and we're going to measure vector B. So let me grab my ruler, and I need my protractor out of the way for now, so goodbye protractor. Okay, and ruler, let's see, I need you to actually rotate around, so we got to actually measure vector B. So parallel to B, that looks about parallel, and so vector B, if we go from the tip to the tail, it looks to be about 3.9 centimeters long. So up here I'm going to move this up. I've got 3.9. I put my mark right here. Wow, that's awesome. Looks like everything comes together right there at that point. And so then what I can do is finally move this guy out of the way and draw in vector B over here. Okay, and so I'm going to make this, I don't know, yellow. Okay, and so vector B gets drawn from the tip of this vector to right where these two marks were, right there. So now I know where the resultant is going to be. So then I draw in my resultant, and I've already got it sitting right here, but I'll just grab it. Okay, so then I draw in my resultant, and I draw it from here to here, and then if I want to know anything about this resultant, I can go ahead and measure it. Okay, and so let me grab my protractor again, and let's see, bring him back. Everything's at 0, and so I can see that this is at 84 degrees, so my resultant is at 84. And if I want to know the magnitude of my resultant, then I'm going to grab my ruler again, rotate it so that it's parallel to my resultant. Let's see, go put this thing over here, rotate, 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 and it looks like that this would be 4.756, yeah, 4.7. 4.7. Okay, and so if it was newtons, if it was meters, whatever those vectors are representing, we just found it. And so it's 4.7 units. Okay, I don't know what we were measuring at 84 degrees. And so it's just like what we thought. Yeah, most of this is up, but it's also a little bit right. And it makes sense it's a little bit right. This vector that we started with is a little bit bigger than this vector, so it's going to win. Okay, it's going to dominate. We're going to go mostly forward or up, but also a little bit right. Okay, so that's the graphical method of vector addition. You use a protractor, you use a ruler, you measure these things out. It's important that you go to scale. Okay, and so there's a couple problems that I want you guys to work in the book on page 121. Okay, and yeah, you actually have to do these with a protractor. I want you to do all the practice problems, numbers 1 through 5. Okay, or 5, 1 through 4. Now, there's a problem there. Number 4 actually says hey, an ant crawling on a sidewalk is moving south and then it's moving southwest. Okay, well, usually we say this way is south and this way is west. Southwest is exactly in between them. This is southwest. Okay, so when you're actually drawing that, it's a 45-degree angle from west or from south, just so you know. In fact, why don't we go ahead and work number 4 together real quick, and then I'll let you guys do the rest of these. Okay, so number 4 says an ant is crawling on a sidewalk. At one moment it's moving south a distance of 5 millimeters. It then turns southwest and crawls 4 millimeters. What is the magnitude of the ant's displacement? Okay, and so I'm going to grab a ruler, and you don't have to use millimeters, right? Millimeters are really small, hard to measure. So what I'm going to do is I'm going to set a scale. Okay, and I'm going to say 1 millimeter. I'm going to set my scale. 1 centimeter on my scale is 1 millimeter in the problem. Okay, and so I need my starting point, which is right here, and I need my ending point, which it says is 5 millimeters south. Okay, so 1, 2, 3, 4, 5. So there's my 2 spots, start, end for the first vector. Then it says after that, it turns and crawls southwest 4 millimeters. Alright, so now I need to be able to measure southwest. Well, first thing I'm going to do is I'm actually going to draw in this vector. Okay, so right along there, awesome, we've got that. Now I'm going to move this out of the way, okay, and I need to put in a southwest, which means I need to measure an angle. Okay, and so here's my protractor again, but I'm going to go ahead and rotate it. Thought I was going to rotate it the other way. Okay, and that way I can measure my southwest. Now you got to be careful if you do this. You might want to establish 90 degrees first. In fact, I probably ought to do that. Okay, mine snaps, and in real life yours doesn't snap to where it should be. So I'm going to rotate it back this way first, just so we can see 90, and I'm going to put a mark at 0 degrees, and that way when I rotate it around I know where 0 degrees is. Okay, awesome. And now I can measure southwest, which is really 45 degrees, and so scroll down a little. Okay, 45 degrees is right here, and so now I can actually go ahead and connect up my 2 lines. Of course, protractor's in the way, so I need my ruler. Okay, and from here, whoops, not there, from there, I want to go this way, in this direction towards my mark, and it said 4 millimeters. So 1, 2, 3, 4. There's my mark. I can connect up my 2 vectors, and now I've got the entire displacement of the ant, but I have to finalize that by drawing in my resultant vector. So I'm going to move this back to the tip of the first one, rotate this around, okay, and now I can draw in my resultant vector from the tail of this one to the tip of the last one. And I guess I never did put my little arrowheads on there, but these vectors are going like that. And so what I get is this vector, and if I want to know its magnitude, all I got to do is measure it. Okay, looks like it's about 8.6. So 8.6 millimeters, and if I want to know the direction, all I have to do is measure this vector again. So I'll grab this, bring it back over, and let's see. Since I know that was south, I can measure this, and it looks to be like this is at, well, okay, now I've got to be careful. Really, I'm measuring from here, which is 0 degrees, so this is 180, but then I'm counting up. So this is 270, 260, 250. Okay, at 250 degrees. Or if you'd like, you could say at 70 degrees south of west. Okay, either of those would be alright. Okay, so vector addition, graphical vector addition takes a minute, but it gets you exactly everything you need. Okay, so finish working those problems. Good luck.